Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and I'm glad you've taken the time to join us today as we look at our topic of how to select an electric torque screwdriver. Now, if you have any questions or any comments, feel free to put those into the chat. We'll have a question and answer time at the end of the presentation. But let's go ahead and jump right into today's topic. And there are a number of different types of electronic screwdrivers for different types of applications. And just as many different types of screwdrivers that are available, there are just as many fastening risks that there are in the actual application process. And some of those risks are due to over torquing a fastener. And if that fastener becomes over torqued and is close to its yield point, any type of shock or vibration can cause that fastener to fail. And then the reverse of that, if a fastener is under torqued, any type of vibration can cause that fastener to completely fail, not holding our parts together. And then we have, again, failure in the process. We also have the human element that's part of the fastening risk. Did the operator accidentally cross thread a fastener? Did they miss them? Did they skip them? And there are a number of different screwdrivers and accessories that help with each of these different types of problems that are associated with the actual fastening risk. Now, one thing that you may hear in relation to a electric torque screwdriver is going to be either static torque versus dynamic torque. This can also be heard as well when we're talking about torque sensors and transducers. But as it relates to the fastening process, a dynamic type of tool would be that creates an RPM during the actual rundown fastening process. And so a static type of tool would be considered a hand tool, whether that is a wrench or a torque screwdriver that is manual. Those would be considered a static type of tool. And the dynamic tool would be those types that are actually creating RPM. And that also produces some type of inertia. That is also part of the equation of the torque delivery for that particular tool. And that could be for an electronic torque screwdriver. It could be for a pneumatic pulse tool or a pneumatic clutch tool as well. So if you do hear that, dynamic torque is dealing with those types of tools that create inertia within the process. Now, why would we select an electronic torque screwdriver? Well, there are a number of different reasons for that. One may be you're moving from a situation where the operator is using a hand tool for a certain application, and there are maybe a number of fasteners, and you want to make it easier for the operator to be able to complete those fastenings very easily without having to introduce any type of twisting or carpal tunnel type of scenarios with the use of a manual torque screwdriver. It could also be that you might be moving from an air tool to a electronic torque screwdriver. And there are a number of reasons for that as well. The air tools seem to be or have a higher rate of decibels to them, so they're obviously louder than an electric torque screwdriver. They can also produce a more particulate through the exhaust system for that, and they are typically only a 1 RPM style of tool. So that may be one reason that you're moving from an air tool to a electric torque screwdriver. It could mean that the application also is better suited for an electronic tool, and then which one am I going to need for that. And so those are a number of different reasons why we would be selecting the torque screwdriver. And to get into the factors that would move us to one particular type of driver, maybe the use of the material that is going through the application. Is this going to be a self-tapping type of application where we're running our fasteners into plastics? What is the density of that plastic? What is the thread for the fastener itself? How is it coarse enough? A lot of these things will then move us to one direction or another within the selection. What type of coatings are on the fasteners? Do they react as it's being or after it's finished? Do those materials once they come in contact, do they change their structure at all? A number of the things that we look at as it relates to material can play a factor. Obviously, if we're looking at the amount of fastening that is going to be taking place, the amount of screwdrivers, or excuse me, the amount of fastenings that we're going to be happening, that can certainly play a part in which type of tool is going to be best for that type of application. Next, we want to look at what RPM are we going to need? Are we going to need a tool that is going to have just one RPM? Do we need to maybe have some flexibility with that application to have maybe an adjustable type of RPM, or is there something else that may be needed for this one particular type of application? Also, does the screwdriver need to be ESD compliant? Is that a necessity for your particular application? Obviously, if we're dealing with electronics and componentry there, ESD may be part of that requirement for that. And then we'll also look at the actual joint itself. There are different joint classifications that that you may hear of or have seen, but typically there are hard joints and soft joints. And hard joint would be considered once the fasteners mate and those bearing surfaces. If that fastener rotates 30 degrees, then that would be considered a hard joint. If it goes up to 720 degrees of rotation once the bearing surfaces have met, that would be considered a soft joint. And so the soft joint application may require a tool that can handle the type of load that a soft joint is going to produce. And so the torque value at a hard joint and the torque value for a soft joint, the tool on the soft joint is going to be working a little bit harder because it's going to be having more load on it for longer until it reaches the final torque and then clutches out. Excuse me. So some other variables to think about when we're looking at the effects that happen during the torquing process. The first one would be if we are introducing a gasket. Just like I mentioned, any type of gasket material is going to cause that to be considered more of a softer joint. And so we may need a tool that's going to be able to handle the soft joint much better. You could also be looking at if there is going to be any type of lubrication that may be added to the fastener, whether that might be thread locker or if it's designed to be oiled. We need to be able to think about that because it's going to reduce the coefficient of friction during that rundown, and we may get a larger clamp force within that particular rundown as opposed to a non-lubricated fastener. So that could be a variable within the torquing process. Again, material, we talked about RPM within the actual rundown itself. If you have a higher RPM tool at a very low torque value, that additional inertia is going to add additional torque to the final output. And so those types of things can, again, be variables within the actual selection that we need to do for our particular tool. And so that's going to lead us to our poll question for today. And we'll go ahead and launch that poll. And so we're looking at what type of electric drivers do you currently use? Are you using a lever to start screwdriver, push to start electric screwdriver, a robotic screwdriver, or some type of cordless tool? So I'll give you a minute here to go ahead and answer that. And I will go ahead and grab a drink of water, and we'll be back in just 1 second. All right. So within our respondents here, it looks like the overall winner in our poll, or the one answered most, is going to be our push to start electric screwdriver, followed by cordless and lever, and a couple of robotic drivers as well. So thanks very much for participating with us in the poll. I appreciate that. And so when we're looking at the different types of screwdrivers that are available, this is kind of where we can talk about what particular tool is good for what type of application. And so our first one we're going to talk about is a direct plug-in torque screwdriver. Now this has the power cord come directly out of the tool, and you go ahead and connect that right into an outlet. This type of tool is really good for a low volume, low duty cycle type of application. Now, the reason for this is the transformer for this tool is built inside of it. And if the tool is used in a really high duty cycle, meaning that the tool will run down, it then needs some time to rest before it goes and does the next operation, to allow it not to overheat and burn up the transformer. And so for a direct plug-in tool, you're typically looking at maybe a second on, 3 seconds off, that type of scenario. But if you're doing a particular fastening job that you want to, again, be low volume, a low duty cycle, this type of tool may be the right choice for that application. And the advantages of this tool are that they're typically less expensive than a different style of tool, and that it'd be a transformer or a power supply type of tool where the transformer is outside of the tool. These types of tools with a transformer give you the ability to have a much higher duty cycle. So they are really good for a high volume, low or high duty cycle type of applications. And these tools can range from very low inch ounces all the way up to about 90 inch pounds or so, depending on the range of tool that you need, and then some of the other things that we'll talk about as it relates to the different options that are available with the different screwdrivers. But generally, a transformer tool is going to be very good for a high duty cycle, high volume type of tool or application, sorry. So the first one option that you have with some of the tools is going to be the ability to adjust the RPM for that particular tool. In some cases, you can adjust the RPM on the transformer. The transformer may have a switch on it that will give you a low RPM or a high RPM. So you just get basically 2 different RPM selections. Or you can move to a tool that will allow you to program a different RPM and go ahead and set that tool. And that RPM increment kind of depends on what the tool is or its range. You could have steps of 50 RPM, or it could be 100 RPM. Just depends on that range. But for the most part, you are typically plugging this a special key into the transformer, then adjusting the RPM, removing that key, and now the RPM is set for that tool. Again, RPM can play a factor into the output of the tool, so that's one thing to keep in mind if you want to use a variable speed RPM type of tool. Next is going to be the ability to have a soft start feature, meaning that we can set the tool to kind of ramp up to its RPM speed. And this may be very helpful if you want to try to avoid any type of cross-thread type of events. The soft start feature allows that to allow the thread engagement to happen at a very slow RPM. If there is a cross thread, it's not going to necessarily, it will not be the full value of the RPM, so it may help to reduce any type of damage that may happen in a cross thread event. But nevertheless, a soft start feature can help with that type of problem if you are facing that. Then, as I accidentally mentioned, there would be a soft stop feature that would be available with some of the different screwdrivers. And the soft stop is going to be very good for those applications where you have a very delicate type of product. And it could be a disk drive. It could be, again, anything where you want to avoid any hard shock or vibration. The soft stop clutch in there is shock absorbing, so it does help with that. So any type of ceramics or anything like that, a soft stop feature is available in some of the drivers as well. And then there are also push to start screwdrivers, as we mentioned within our poll. Most of the screwdrivers are available in either a push to start or a lever to start. Now, you may see a real desire for a push to start type of tool, especially if you're moving from an air tool to a electric tool, because often the air tools are a push to start type of tool. Lever to starts are usually better for those applications that any type of damage to the actual part, or if the tool isn't properly engaged with the bit and the fastener. If you are using the push to start and that is not the case, you may be damaging the product accidentally, having the tool slip off the fastener. So a lever to start, just make sure that the operator is ready to go and they can go ahead and pull the trigger when they're ready, and there isn't any type of mistake or accidental push to engage the driver. But a lot of people like them. A lot of operators like them. It just depends, again, on the application and if that's going to be the right fit for that particular tool. Now, another thing to consider with the different types of tools are going to be those with brushes and those without. So a brush motor versus a brushless, and it's quite simple. There aren't any brushes in a brushless screwdriver. So, I'm sure everyone might be familiar with how this works, but typically in an electrified motor, within its circuitry, we have carbon brushes, which are on the commutator there, and a set of magnets that are causing either a push or pull effect as power is applied in a certain direction to go ahead and rotate our shaft. And this would be the use of the carbon brushes. that again are in contact, and those have some type of force that are being pushed on. And as the motor spins, those brushes will eventually wear, and those typically will produce some type of particulate. But this is just an example of a motor, and with the brushes there that are on the commutator as providing the completion of the electric circuit as it rotates through or as the motor rotates. Now, a brushless motor works a little bit differently. The components are electrically controlled, and the magnets there, or the housing, is on the outside. And so as different forces are attracting or pushing the magnets, that is what's causing the output shaft there to turn. And so there isn't this constant force of the brushes on the actual motor shaft itself. Again, now creating no particulate, and typically lasts longer because there's no maintenance or anything like that that's needed for that particular tool. So if we take a look at what that may look like over time, you can see on the left there is a tool that is a brush type of tool, and the inside of that housing there is kind of getting filled up with the remnants of the carbon brushes. And on the right is a brushless tool where there's again nothing that's being generated as far as the particles are concerned with that type of housing. So that'd be one of the differences between a brush and brushless screwdriver. But typically, the same tool may have two of options in it, may have a brush or a brushless motor. The obvious advantage to a brush type of tool is that it is typically less expensive than a brushless motor. And so if you are looking to save a little bit versus the brushless, then the brush motor or brush tool will work just fine. And within that type of or environment where we want to use a clean room type of tool, we can hook up different vacuum ports to a particular tool to help remove any type of particulate that may be generated in there for that. In this example here, you see there's a port on the side of the tool that is moving any particulate out of it out through the vacuum system. And then there's also a vacuum pickup at the bottom of the tool, or the bit end of the tool, where the bit is surrounded by a mouthpiece or sleeve that will allow us to go ahead and suck up a fastener into the tool, so the operator does not have to go ahead and put the fastener on the tool. So a vacuum pickup type of tool can help within those really small type of fasteners that may be an issue. So a vacuum pickup can certainly help in that scenario, where the operator can move the tool over to a screw presenter or a shaker tray and grab the fastener and then go ahead and engage that in the part. So that is another type of almost an accessory to help with that. But a vacuum pickup system will certainly help in those types of scenarios. Some other types of screwdrivers are going to be those that are robotic, that can fit on either or mounted to a robot arm or a cobot, and that are then operated by an assembly process. And so that's another option that might be available to you. There's also cordless tools that may be helpful. Typically, these cordless tools are either going to be in a right angle configuration or a pistol grip, like you're seeing here. This is our transducerized battery tool, but that is a scenario. In some cases, you don't see it too often within the torque. You may have an inline battery tool, but those typically aren't going to allow you to go much higher in torque because of the fact that it may actually spin in the operator's hands. And then you're putting it on an arm, which kind of defeats the purpose of the battery. But nevertheless, the cordless drivers are available as well. And then finally, we have the DC controlled type of tools, and so these are have a different clutch mechanism built into them, obviously, than an electric torque screwdriver. However, they do give you the most control and most flexibility to be able to handle most entirely applications within the ability to program what happens from when you pull the trigger until the final seating is complete. There are some really good advantages to using a DC tool. We do have a lot of other webinars where we're talking exclusively about these tools, but in the context of figuring out which tool might be best, these tools do allow you to have a number of different presets. You can have up to 15 or so in this one that is expanding here soon. But you do have that ability to have 15 different drivers basically that you can use at any time within the limits of the range of the tool. And so that may be a consideration for you if you've got multiple types of fastenings and multiple tools. It may be more efficient and easier for you to have one tool that can do a number of different jobs and having the other tools there. Because a typical electric torque screwdriver has one torque value that it's set to. And then the DC tool allows you to be able to have multiple different presets. Again, we have a ton of different content and videos on the DC tool, and be sure to check those out if you are interested. So some of the accessories that I mentioned that may be helpful with the use of an electronic torque screwdriver. One, there is going to be a pistol grip attachment. So if you want to change the orientation of the tool from inline to a pistol grip, you can add an attachment to that. If you want to change the orientation to a right angle type of scenario, you can add a right angle adapter onto the end of the tool to do that. With that type of thing, you want to make sure that we're testing the tool with the setup and the right angle configuration. A tool balancer is another item that is very, very helpful. And there are a number of different types of configurations of those, but this again allows you to suspend the tool to be able to keep it off the bench and keep it safe from useless damage. Another accessory is going to be the screw presenter. This allows you to put fasteners into a hopper. That hopper then will feed fasteners to the end of the unit, allowing the operator to either pick that up via a vacuum pickup, as we talked about, or a magnetic bit if the fasteners can be magnetized or if the bit can be magnetized. And we grab that fastener and then go ahead and move to the application. Torque arms, again, can be very, very useful. They typically you'll want to use those in a higher torque that may be generated. This, again, helps to alleviate any type of carpal tunnel or repetitive motion injuries. And the torque arms are available in a number of different configurations. From telescoping arms to the articulated arm that you see here. But they're very, very good also at the very, very low torque values, because any type of possible side load from the operator. Any type of an additional force to that may change the torque output. So if we have the tool on an arm where it is secure, if it's in a vertical type application where we're preventing any type of side load, we're getting 100% transfer from the tool to the part. And that's really critical, especially in a very, very low torque type of environment. Next would be a torque cover. This goes around the cone or adjustment mechanism on the tool to prevent that from being accidentally changed by the operator, or the operator changing it on purpose. But that's another story. And then finally, you have screw counters that can be connected to a transformer. And then that is keeping track of how many fasteners the operator has done. And this could be really useful in a scenario where you may have 50 or so fasteners within one assembly, and you want to count how many are being done, and you can program a number of different settings for that as well. So those are some of the accessories that you have available to you as well when we're looking at the different torque screwdrivers. So that is going to go ahead and lead us into our demo section here for today. And basically what I've got set up is a torque screwdriver, or excuse me, a torque analyzer. This is our Easy Torque 3i. We have a rundown adapter on here, and basically the rundown adapter allows you to be able to simulate the tool at its running RPM. Now, if we were to just stick the rundown adapter into the transducer, turn it on, it's going to immediately clutch out, and it's going to produce a value, but that value is going to be different than if we were to go ahead and let that tool, run to its RPM. So we have a rundown adapter, and it's very similar to our other analyzers, but because we're dealing with such a small torque value, we have just introduced the 1i, or 1 inch-pound analyzer. This is our 3 inch-pound analyzer, and we also have a 5 to go with the rest of our models. But this would be a 50 inch-pound transducer to go into either our reaction style transducers or our LTT product as well. But just to let you know, this is our soft joint rundown adapter here. And I've got a couple different screwdrivers here, but this would be one driver that we have. And you can see here that this is a brush style tool. It's because we have our brush ports here. If we go ahead and open this out, we can pull out those brushes and replace those if needed. And then this would be a brushless style version. Again, there's no ports for the brushes. This one also gives us the ability to set the RPM and be able to initiate the soft start if we like. But these particular drivers are controlled by a clutch mechanism that allows us to change the torque by how much tension is placed on to a torque spring. Now, you may see one tool may have 2 different springs, or could be maybe even 3 different springs, but they're usually colored springs that will produce a different rate of torque. So if you do that or have to change it, you can go ahead and do that. But this gives us the ability to have one tool that can reach different torque values with different springs. And there are also little reference marks that are available here on the inside of the tool that will allow you to set this cone to a certain value here. And so that is, again, just a reference point. It's not an actual torque value. And then if you get it set correctly, you can go ahead and put down, there's a little set screw here, or you can put your torque cover in here. There's threads in here. We can go ahead and put that torque cover on there. So if we want to go ahead and use a torque analyzer to go ahead and set our tool, I have one of our drivers here. We can go ahead and run this down and see what we're getting. Go ahead and let it warm up here. Okay, if, for example, we want to go ahead and try and set this tool to, say, 1.5 inch-pounds, we'll go ahead and change our target torque here to 1.5. And come back to our operation screen. This now gives us that target is at 1.5. If I go ahead and run this down, you can see we're at about 1.3, 1.4-ish. So I can go ahead and I can turn the cone here a couple of clicks, and this is going to allow us to increase the actual torque value. So you can see I've gone a little bit over, so no problem. We can come in and we can back that off a little bit. And there we're kind of dialing it in better to where we want this tool to be. And if we go through the actual process here, set our tool, then we can go ahead and put that tool out in use. But that's how the tools function, with that clutch mechanism, the spring in it, and then also how you would set it up on a torque analyzer as well. So that's going to bring us to the end of today's presentation. That's going to lead us into our questions and answers. So let's see, Chris, do we have any questions?
Morning, Dave. First question we had was, why would you use a soft start function with the power tool?
So as I mentioned, the soft start feature allows us to be able to start at a really slow RPM and move up to the operating RPM. And that's to help to try to make sure we have good thread engagement with the fastener, so we can help to prevent any type of cross threading. So if you have a really fine thread, that might be a super helpful feature to have a softer start to that, to make sure that the thread engagement is correct, and then up to the operating RPM.
All right, Dave. Another question we had was, what's the difference between the tool's accuracy and repeatability?
So you could have basically a tool that is very, very accurate, meaning that it is very, very repeatable. And you're getting a really close group of readings that it is producing. Accuracy is going to be how close are you to the actual target that you're looking to achieve. And so you may have a tool that's not very accurate, but it is very repeatable. So you need to make some adjustments to move that that repeatability closer to the accuracy point that you're looking to achieve. Now, you may have a tool that has a wide range of repeatability, but on average, it's very accurate because we're looking at averages. But our goal is to have a very repeatable tool that is also very accurate. So that's kind of the difference between repeatability and accuracy.
All right, Dave. Another question that we had was, is there a device or something that you can use to help detect cross-threading events when using a power tool?
So you can use in our DC tool, we have a feature that will notify you if there has been um, torque achieved before the proper amount of turn or angle happened within that fastening process. And so, let's say, for example, it takes 1,000 degrees of rotation to fully seat a fastener. We can tell the system if we get a torque up v- value, and it is less than, say, 500 degrees of rotation, produce an error and let the operator know that um, event happened. And a cross thread event is going to happen right at the very beginning of the operation. And so that will indicate that the fastener has been cross threaded um, with that. You
All
could
right,
also
Dave.
do it.
That looks like the.
Oh, sorry, Chris. You could also do
Go ahead.
it
Oh,
with the use of our screw counter Scout. The Scout will do the same thing, but instead of measuring it by angle, it measures it in milliseconds of time during the actual rundown. So if and we can create what is going to be an acceptable window limit within the amount of time it normally takes to run a fastener down versus the cross thread event. Again, the cross thread event is going to happen right at the very beginning. And so the Scout will tell us that if a cross thread event happened, it will give us a no good for that fastener. And then the operator can go ahead and correct it. But that would be with the use of a electric clutch torque screwdriver.
all right, Dave. Thanks. That looks like that's the end of our questions for today.
All right. Thanks so much for everyone joining us on this month's webinar. We look forward to seeing you again. Have a great rest of your day and a good weekend, and we'll see you next time.